Getting back to this idea of the patterns, this is very important. And you may see something similar to this in your lecture videos. If I monitor the rate of the reaction versus the concentration of the reactant, let's just call it A, and I know that this reaction is first order. If the rate is 10 when the concentration is 2, I'm just trying to come up with easy numbers, then if and this is like trial 1. If I run a second trial where I change the concentration to 4, if I've doubled the concentration, because the rate law is rate equals K times A to the first power, that means I should calculate a new rate, which is also times 2. My new rate should be 20. Since I doubled the concentration, the rate constant stays the same. I doubled the rate. I could work this the long way as we did above, where I could calculate the K for trial 1, then plug that into trial 2, and I could figure out if this is what I'm trying to find, I could figure out that that was 20. But I see the pattern here. If I change the concentration to 10, all right, for example, let's say I run a new trial, trial 3, where I change the concentration to 10, from here to here, it's the same reaction. I went up by 5. 2 times 5 is 10. I now have multiplied the concentration by 5. The rate will also be by 5. I should find the new rate 50. It works that way because of this equation. If I look at a second order process, it gets a little more complicated. All right. I have a new reaction, so let's call him B. And this is trial 1. And I run trial 1 with the concentration of B of 5, and I find the rate to be 20. I'm just totally making up numbers. I know that the rate law is rate equals K times B squared. And I could calculate K for trial 1, and it'll be that K no matter what. But let's say I run trial 2, and I change the concentration to 15. I could find the new rate by plugging back into the rate law with that K I calculated, or I could recognize that he went up by 3, but you'll notice that he's squared in the rate law, so the rate is going to go up by 3 squared. The squared is that squared in the rate law. So the rate is going to go up by 3 squared. So 20 times 3 squared is 180. My new rate is 180. That's exactly what you would get if you solved for K in the first trial and used it to calculate the rate in the second trial. But recognizing that pattern is important. If I change my new rate, if I make a new rate, let's say I do trial 3, and my new rate is 10, well, that rate went up by 2. So that concentration. Let's say I changed my concentration to 10. That concentration went up by 2, which means my rate goes up by 2 squared. So the squared, again, is that order, and 20 times 2 squared is 80. And that's exactly what you would find if you solved for K in trial 1 and used it to calculate the rate in trial 3. And just to be clear, let me make sure this times 3 is because that's times 3. This times 2 is because that's times 2. That one's a little hard to see. Let me make it a little darker. That times 2 is because that's times 2. Gets only a little bit more complicated if you have a third order, in which case the rate is equal to K times the concentration. Let's go with C raised to the third power. And so let's run, keep those on there. Rate and concentration of C and trial 1. And let's say we make the concentration of C 6. and we measure experimentally, the rate is 400, whatever, making up numbers. If we change the concentration of C, let's change it to 36, which means we went up by 6. Notice how I'm not using nice even numbers. I'll do this for you. Nice even numbers. 36 times 6 is 36. Because of the way the rate law works, and this factor is cubed, the rate will go up by 6 cubed. The rate will go up by 6 cubed. And that cubed is because of the cubed on the rate law. And so 400 times 6 cubed is, let me write it in scientific notation, 8.64 times 10 to the 4th. All right. All right. So that's the new rate for trial 2. Again, I can get exactly the same answer by solving for K in trial 1 and plugging it back into the equation, but recognizing this pattern is important. And again, just to be clear, this times 6 is because that's times 6. The cubed is because it is third order. Let's say I run a trial 3 where I change the concentration to 24. Well, 24 is times 4. 6 times 4 is 24. What does the rate do? Well, it goes up by 4 cubed. Again, the cubed is because of the order, and the times 4 is because of the times 4. And so let me calculate that. 400 times 4 cubed. Oops, I didn't do that right. Again, let me put it in scientific notation. I get 2.56 times 10 to the 4th. So recognizing those patterns is important. We have one more, I know we're getting close to the end. This is what you're going to be doing in lab today. You're going to be looking at these patterns. We have one more order that we haven't talked about. We will not go higher than third order for this class. Can there be orders higher than third order? You betcha. We're not going to go higher than third order for this class. We're pretty much keeping it to that. We're pretty much keeping it to that. If we were going to fourth order, though, we could see the patterns here. There is another order, though, that we do have to deal with, and that is zeroth order. And I know you saw this in the lecture videos, and you're going to watch about it more, but there are certain reactions that behave as a zeroth order process, which means the rate equals K times the concentration, let's call it D, raised to the 0 power. And you may recall that anything raised to the 0 power is 1. So this is the same thing as rate equals K. The rate equals a constant value. The rate doesn't change as you change the concentration. So in this particular case, if I measure the rate versus the concentration of D, and I do trial 1, and I make the concentration of D 10, and I find out the rate is 50. All right, I didn't do that before. All right, and then I change the concentration of D to 20, I double it, the rate stays 50 because the rate doesn't change based on the concentration change, because the rate's change is times 2 raised to the 0 power, and 2 raised to the 0 power is 1. So 2 raised to the 0 power is 1. So the rate doesn't change. The times 2 is the times 2, but it doesn't matter. If I change the concentration to 14.6, the rate is 50. If I change the concentration to 2.5, the rate is 50. It doesn't matter how the concentration changes, the rate stays constant in a zeroth order. All right. So now we can use those patterns to answer the question about, well, how can I figure out, oops, I put that page right in the middle of that. Let me grab the header. To answer the question of, well, how can I figure out a rate law? And that's what we're going to do next. And we'll do one of these. This is just like you're doing in lab today. It's a little bit more complicated in lab. You'll see that in the lab write-up and the pre-lab. This is how this works. All right. So the balanced equation for a reaction, this is question 17, is 4x plus 3y yields p. So there is an x and a y in that reaction. And so my table includes information for both x and y. If I had a third reactant, there'd be a third column. In lab today, you got 3 reactants, 3 columns. And somebody went into the lab and measured the rate for trial 1, 2, and 3, where these are the concentrations. And this is exactly what you're doing in lab today. You are changing the concentrations and measuring the rate. And of course, you're watching that happen. So you're changing the concentrations and watching the rate. So trial 1, we have concentration of 0.2 and 0.02 and 0.06. All right. And this is the rate we measured. In trial 2, notice that we kept the concentration of X the same. That's so we could focus on what Y is doing. You always need to keep the concentration of somebody the same so that you can focus on what Y is doing. And from trial 1 to trial 2, Y is doubling. It's going by 2. All right. Now, if we knew if this was first order or second order or third order, we would be able to predict the rate in that block. But that's not the point of this. The point of this is we measured the rate. Now we're trying to predict what the order was. So we need to analyze, well, what happened between trial 1 and trial 2? How did it change by? This is times what amount. Since you can't tell, if you look at these numbers, it's not nice and even. To tell by what amount, you're going to take 2.72 times 10 to the minus 2. You're going to divide it by 3.40 times 10 to the minus 3. You're going to divide the second one by the first one. Just like if I divided 0.12 divided by 0.106, I'd get the times 2. So this is basic math, but it may have been a while since you did this. I'm trying to figure out what this is times. So this is 2.72 times 10 to the minus 2 divided by 3.4 times 10 to the minus 3. This is times 8. All right. And now I'm trying to see that pattern. If the rate goes up by 2, I did it again. If the concentration goes up by 2, the rate goes up by 2 raised to what power? Raised to the x. Well, I'm trying to figure out what, I don't want to use an x, what the power is, raised to the p, the power. And 8 is equal to 2 cubed. Try it for yourself. 2 times 2 times 2 equals 8, which means that it is third order with respect to y. So I am observing that pattern backwards from what we were doing above. All right. You're going to have to practice these and watch the lecture videos and where we practice some. Let's go ahead and do X before we run out of time because we got 3 minutes left. If I look at trial 3, X is 0.08 and Y is 0.06. You'll notice from here to here, I kept Y the same. That's so I could focus on what X is doing. So from here to here, I'm focusing on what X is doing, and from here to here, I'm focusing on what the rate is doing. So X concentration is going up by 4. 0.08 divided by 0.02 is 4. Let me calculate what the rate is going up by. So 1.36 times 10 to the minus 2 divided by 3.4 times 10 to the minus 3, and that gets times 4. And so times 4 for the rate equals 4 raised to what power? That's 4 to the first power. That is times 4 to the first power, which means it is first order with respect to X.